Okay, so we're going to take a look at the Miller compensated common source amplifier. Now, a lot of the time you can have a common source amplifier, and the common source itself is rather simple. But Miller compensation is when you add this capacitor and resistor in series from the gate to the drain. Now, as you may well know, when you just have one capacitor from the gate to the drain, it can make the algebra quite annoying. And in those circumstances, you might be tempted to use Miller's theorem to put the capacitor on the front and on the out. But Miller compensation adds this extra resistor in that feedback relation. So you may be wondering, why would you do such a thing? And how does it actually help you? And what does it actually do to the circuit? And I've seen a lot of people get Miller compensation and Miller's theorem confused. They're slightly different things. Now, having this capacitor will induce a Miller effect. It will look like a bigger capacitor by virtue of its feedback setup. But importantly, it does something to the poles and the zeros. So just look here for now. Don't look at all the algebra. We'll get to it. So what we're going to do is we're going to find out exactly where the poles and the zero is for this circuit, right? Because if you just use Miller's theorem on it, you'd conclude there's only two poles and zero and no zeros. But that's not correct. So I've drawn the circuit here, and you'll notice I've drawn the load capacitance in red. You'll see why that's the case. But bear with me. For now, in our initial analysis, we'll ignore it, but we'll get to that. So here's our small signal model, right? Very simple. Drain to source resistance in parallel with RD, because the VDD goes to zero. This is a rather more complex subject than a normal small signal model, but the small signal model itself is pretty simple. So, and then here's our load capacitor. We know our VGS is just Vn because this is the gate. That's the source. Great. That's in parallel with Vn. We only need to write a single KCL to do all the circuit theory we need here. And we'll do it at the out node. And we'll write all the currents that's going out in each branch. And for now, trust me, we'll ignore the load capacitance. So I'm also going to abbreviate RDS parallel RD as just R, because I don't want to have to write RDS parallel RD 100 times. So the first current in the branch is just V out over R. That's simple enough. The next current is GM VI, of course. And then the last term is this tricky one, which is the current through the added feedback path. Oh, and we're going to ignore all the parasitic capacitors in the circuit, because if you had to include that, it would make this a bit more annoying, because then you'd have a CGD in parallel with all that, and, forget that. We don't want to go there. Okay, so this is the term of the current going from the output to the input, like this, right? That's why you're dividing by the impedance of that series branch, which is, of course, 1 over SCM plus RM on the bottom. And now this line here is the only KCL we really need, okay? Literally, all the rest of this is just algebra. And then when we find the pole locations, we'll discover, surely, how the circuit responds. Okay, so we do some factoring. You rip out 1 over plus RM and 1 over R. You put VI on the other side. And since this is a minus, that becomes a plus. Since this is a plus, that becomes a minus. You factor out the VIs and the VOs. You divide by the VOs and the VIs. And you get this right here. This is technically the transfer function. Done, right? Well, no. Because it doesn't really tell us anything. Sure, algebraically, we've now found it, but we need to get it into a form that is more digestible and gives us more knowledge about what's going to happen. So we just have to do a bunch of algebra. So I'm going to multiply by these denominators over itself, so you can bring it in. Then you FOIL it out. Then you multiply. Well, this is just how I did it. Obviously, there's many ways to do this. Then you multiply by this again. Now we have a form that's a little more a little more palatable, and the units are unitless in all the categories we can see. We have 1 over ohm times ohm, 1 over ohm times ohm, 1 over ohm times 1 over ohm times ohm. So that's unitless. You have 1 over ohm times ohm plus 1 over ohm times ohm. So it's unitless over unitless. And that's pretty good, but we're not quite there yet. So we bring out the R's and we factor those out. And now we have something resembling what we want. Okay? We have the R, we have a zero term, clearly, and we have a pole term. Now, this is where we go back to the capacitor, right? If we had included the capacitor, then this V out over R term would have to be V out over R in parallel with 1 over SCL. And that would make the algebra a little more complicated. So instead, what we're going to do is factor out the R and recognize that since the capacitor is in parallel with this resistor, we need only take everywhere we have an R term and turn it into this. Because surely, if it is in parallel, then it would have been completely proper just to write 1 over SC parallel R everywhere I already wrote R, right? And really, we're just saving a lot of steps doing that. So I factored out the R in front. We know what a resistor in parallel with a capacitor is. It's 1 over SC over 1 over SC plus R, which of course is 1 over 1 plus SCR, right? Great. So now we have this term here. And I like to write it this way. It's convenient because now one of the poles is, or what looks like a pole is preeminently jumping out at you. And of course we had to turn this R, this one here, into R parallel SC, right? Okay, great. Now we do a little bit more algebra, and we keep simplifying, we keep foiling, we keep dividing, and we bring it all out, and now we have an S squared, we have an S, we have an S, we have a 1, we have an S, and we have a unitless on the top. And this R is the actual R. It's not our fake R from before. Okay, great. Now we're going to turn it around and analyze the poles. Okay, great. Now, all I've done is rewritten these and factored all the like terms together. So we go S squared, some constant times S squared plus some constant times S plus some constant. So it's just in a quadratic equation. Because remember, the finite poles occur when the denominator goes to 0, and the finite zeros occur when the numerator goes to 0. So all we're going to do is now solve when the numerator is 0 and when the denominator equals 0. And that will tell us what the zeros and what the poles are. Now, we know because we have a first order S term on the numerator, we have a second order S term on the denominator, the transfer function has to look something like this. Great. We know how we can find A naught. We can find A naught just by setting S equal to 0 because we know we have no zeros at 0. Great. Then, when we find out where the numerator and the denominators are equal to 0, we will have found the poles and the zeros. So, we use the quadratic equation on the denominator, and this is why I've highlighted this as A, this is B, and this is C. Because then you could just say minus B plus or minus root B squared minus 4AC over 2A, right? That's just the quadratic equation. And this is literally just a substitution of that. And sure, there might be some way to simplify this if you assume one term is greater than the other or whatever. That's not really the point. The point is, these are the pole locations. And, you know, maybe I made some mistake, but we'll get to the point. If you find an algebra mistake, let me know. I don't think there is, though. So then if we want to find A naught, we just say S equals 0, right? And we get, well, let's see. This turns to 0. This turns to 0. This turns to 0. This is divided by 1. So we get S times minus GM, which is the only thing left, divided by 1, which is minus GMR. Great. And what does this tell us? This is exactly what the gain in baby circuits will teach you when you see the common source amplifier for the first time. It is minus GMR, when you have no capacitors, no poles, no compensation, nothing. Because all the capacitors in the previous circuit are open circuits. And that sends you exactly to what we know that the gain of a common source amplifier is. So we're probably onto something with the transfer function. Great. Now, we're going to find the zero location. Let's see. Where did I find that? H, SC, GM, minus GMR, SP, H. Well, you would just have to set this equal to 0 on the top. Oh, okay, yeah. So I wrote the limit here because I was messing with it. Let's ignore that for now. Because we don't want that. Okay, so you take the numerator, you set S equal to SZ, you set the numerator equal to 0, you do some algebra, you'll find that SZ equals this. And this unit makes sense because this is GM, which is 1 over ohm, times CM. So this is ohms times capacitance, which is what you want, or under 1 over ohms times capacitance, because GM/RM is unitless. So this is unitless, right? Great. Now, we want to do a sanity check real quick and say, hey, what happens if RM equals 1 and CM equals 0, right? So I'm saying, hey, get rid of the Miller compensation. Show me what we actually get. Well, if you do that, the 0 goes to infinity because, guess what? RM equals 1, so this is just a 1, but CM is 0. You're dividing by 0, so SZ will go to infinity. So there's no finite pole, no finite 0. That should say 0. No finite 0. If there's no Miller compensation. Great. Now, if we say that CM equals to 0, we can take a look at our transfer function again up here. And this will go to 0, this will go to 0, this will go to 0, but not this. And this will go to 0, which will lead to this transfer function. And what do you know? That's also the exact transfer function if you only had the load capacitor. For some reason, I started writing C instead of CL here. I called it CL on the other page, but it doesn't matter. So this would be our transfer function, finally, if there was no Miller compensation. So we now have all the information to make the transfer function for the Miller compensated and the Miller uncompensated common source amplifier. And, the pole locations are a little nasty for the Miller compensated one. The takeaway, though, is that when you have the normal uncompensated one with this transfer function, you just have one pole. And that pole is set by R and C. So you get a simple low-pass filter, right? Now, when you Miller compensate, you introduce a pole and a 0. And you can place that position of the 0 and the poles accordingly. So you get more controllability on when you want your dominant pole and when you want your non-dominant pole. You also get to place your 0. Because notice the location of the 0 is highly controllable. Because you have direct control over what RM is and what CM is. GM is also picked by your bias point, so you can also tweak that, of course. But the fact that it's directly dependent on CM and RM is quite powerful. The other thing you'll notice is that what it will do is it will take the original pole location and split it and send one pole down, send one pole up. That's what these arrows are showing. So really, that's why you Miller compensate. It gives you more controllability over the transfer function, which is quite cool. Not to be confused with Miller's theorem. So, that's Miller compensation. Now, of course, this derivation is a bit tedious and a bit cumbersome, and this is really the whole point of it. But, I think having the mathematics in front of you gets the brute force point across in a way that just normal explanations really won't do. That's it.